Okay, today we are going to be talking about Chapter 5, which is Atomic Absorption Spectroscopy. So if you remember at the beginning of Chapter 4, I told you we can talk about spectroscopy in terms of being for atoms or molecules. We can talk about it as absorption or emission. We can talk about it by the kind of light we use. So Chapter 4 was the absorption by molecules of UV vis. Chapter 5 is the absorption of atoms by UV vis. And we abbreviate that AAS. Okay, now this spectrometry tells you that this method is a quantitative method. It's going to answer the question, how much? And there's actually two types of this. You can see that here, the LS-AAS and CS-AAS. So what do you think the LS and AS stand for? Okay, remember back to Chapter 3, line source, continuum source. Okay, so we're going to focus on line source because that's the most common. That's the type you've done in the lab. Continuum source is a more powerful method, but it's also a very expensive instrument. So I'll mention it briefly, but again, our focus is the line source AAS. Okay, so we're switching over from molecules to, so the primary thing that we use this method for is to measure the concentration of metals and metalloids. Okay, so comparing molecules and atoms. So remember in molecules, we talked about you get these broad bands because you have vibrations and rotations. Now in atoms, when we talk about electronic transitions, we don't have vibrations or rotations. So we just have these lines to look at. Okay? So we get what are called line spectrum. Okay, so this AAS, the basic principle is it's the absorption of light, okay, a discrete wavelength. So that means, a wavelength that corresponds exactly to the energy difference by a ground state atom in its gas phase. So notice, this is going to be different. We're going to need to get the atom into the gas phase and to be as a single atom. So to do that, we have to do a process called atomization. So atomization is the process of taking your original salt of a metal ion and converting that metal ion to a gaseous metal by itself. And we're going to talk about how do we do atomization. So that's much different than molecular spectroscopy, where we just put it in a solution and measure it. Here, we're going to have to turn it into an atom. So there's going to be some extra parts to this instrument. Okay, as I mentioned, this method is almost exclusively quantitative. Okay, it answers the question, how much? It does not answer the question, what is it? Okay, one reason is this method is a single element method. This method can only measure one atom at a time. So of course it can't say what is it, because if we don't know what it is, we can only measure one at a time. In addition, you have salts that have different cations. So if we had, sodium hydroxide and sodium chloride and sodium sulfate, we can measure sodium, but we can't tell where it came from. This method only measures that metal ion. So not a qualitative method, but it is a powerful quantitative method. Okay, so what's the process? Okay, so we need to get the sample into the gas state as a neutral atom. And that neutral atom can then absorb light. And then that electron is going to go to an excited state. So as I already mentioned, these electronic transitions have no vibrations, no rotations. These are atoms. So the bandwidth is actually going to be very, very small for these absorptions. Remember in the last chapter 4, molecular absorption, we got these broad peaks. Here, we're not going to get broad peaks. We get very, very narrow peaks. So, for example, if I have sodium, okay, we know the ground state configuration of sodium is a neon core 3s1. So what we're talking about for absorption is it's this outer electron, that 3s electron, that's going to a higher energy state. Okay, what's a higher energy? Well, one of the higher energy orbitals, 3p, 5s. Those are the kinds of transitions we're talking about for atoms. And in P chemistry, they can actually develop these charts to show you the different transitions. So notice this is the one for sodium, and notice here's that 3s electron, and it can absorb up to 3p, or here they show it going up to 4p, and there's some even excited electrons that absorb to higher. So these are all the different possible transitions that you could have for an atom. Okay, now we said these transitions are going to be narrow lines. So for example, this might be what this partial spectra of mercury looks like. So notice each one of these lines, very narrow lines, each line corresponds to a different transition. It's one of those valence electrons going to a higher orbital. And sometimes we'll say that atomic spectra look like this. Actually, these lines are not really just lines. They have a little bit of bandwidth, like this one is a little bit more accurate for what we'll see for the spectrum. But notice, these look broad, but look at the scale. This is only 2 nanometers. So these, again, are very thin lines. Okay, now almost all of the transitions that we actually see are from the ground state, okay? And what that means is there's actually very few atoms that are in excited states. You can actually calculate how many atoms are in an excited state using this equation. This is called the Boltzmann distribution. You've probably seen this in another chemistry class, or maybe even physics. Now, we're not going to use this equation, but I just mention it because this equation gives us useful information. So here's all the variables defined. But if we were to do this calculation for, say, a zinc atom at 3000 degrees K, which is the temperature of a flame, so this is hot enough to atomize a sample. Notice that only one atom out of every 10 to the 10th is in the ground state. For sodium, it's a little bit better, one atom out of every 1,000. Okay, but what this means, again, is there are very few atoms in the excited state. Most atoms are in the ground state, so most absorption occurs from the ground state. So what that means is that actually the number of absorption lines that we might have is actually quite limited. So if we go back to this figure and we say, well, sodium can have all these different absorption lines, but actually the only ones we're going to see are the ones that start here from 3s, because there's very few electrons in the excited states. So there's going to be a few absorption bands for each atom, but not lots and lots of different ones, just a few. Okay, now I mentioned that these bands are very narrow. We said we need exactly the right amount of energy to go from this ground state up to an excited state. You need the exact amount of energy. But it's not zero, the line width is not zero, but it is very, very small, about 0.002 nanometers. Okay, so these are really thin bands. Now, why is this important? Well, it's important for two reasons. One, it means that there's no overlap between the lines. These lines are so narrow, it means you can have lots and lots of different lines. Now, for line source AAS, what we're talking about in this chapter, that's not important. We just said there's not going to be lots and lots of lines, and we can only measure one element at a time. This would be important if you were doing emission or if you're doing the other kind of AAS. Okay, but this first reason for this chapter is not important. However, the second reason is important. These narrow bandwidths mean we have to design the instrument so we can monitor these narrow bandwidths. The instrument's going to have to be a little bit different than it was for molecular absorption spectroscopy. Okay, so now with that little bit of background, let's now take a look at the instrument for AAS. I'm just checking all the chat to make sure. Okay. All right, so remember, for any kind of spectroscopy instrument, we said we have these four basic parts. We have a radiation source, so we're going to have that for this. We have a sample holder. Now here the sample holder is going to look quite different. The sample holder actually we have to get the sample into the instrument, and then we have to atomize it, turn it into a single atom in the gas state. We're going to need a wavelength selector. We're going to need a detector, and then of course the computer device. So same parts we've seen, but they're going to be a little bit different than we saw in chapter 4. Okay, so let's start with the radiation source. All right, so in chapter 4, we talked about Beer's law in some detail, and we said for Beer's law to be true, you must have monochromatic radiation. But remember, we never have monochromatic. We always get a band of light from the source. So we said, how do we get around this problem? So remember, for molecules, we said we always measure up here at the top of the peak. We always measure at lambda max. Okay, and we said there's two reasons we always measure at lambda max. One is so that we follow Beer's law. The other, that's where we're going to have the biggest signal. Okay, now we said if we don't measure at lambda max, then we're at a place where the absorptivity is changing quickly and we will get a very bad calibration. It won't be linear. And we said, you know, we can do this as long as the bandwidth of the monochromator is 1/10 of the bandwidth of the peak. And we said usually for molecular instruments, the bandwidth of the monochromator is 0.3 to 4 nanometers. So my peaks can be 3 to 40 nanometers wide, and usually it is. Okay, but now as we turn to atoms, remember we said a typical atom bandwidth is 0.002. And if we have a really good, expensive monochromator, we can get the bandwidth smaller to 0.1. But notice that this monochromator bandwidth is much, much bigger than the line bandwidth. So if we try to use one of these continuum sources, we're going to get a horrible result. We'll get very poor sensitivity. So this slide just shows you this point. So here's the bandwidth of light from the monochromator, and here's a molecular peak. And remember, we measure up here at the top, and so the absorptivity is not really changing up here at the top of this peak. So we're okay. And now if we try to use that same light for an atom, okay, remember the atom is a very small line, and you can see here that you know, a lot of this light is going to be wasted. And there we go. Sometimes I lose my mouse. Sorry about that. There we go. Okay. So, you know, if I'm measuring right here, I'm okay. But if I'm measuring here, that absorptivity is going to be really different. So I'm going to get a bad result. And in fact, this picture makes it look better than it is. The true situation is more like this, very thin line. So again, if I measure here, I get a great result. But any other place, even just a little bit off that line, and there's no absorbance. So I'm going to get a horrible calibration. So we cannot use a continuum source for AAS with a typical instrument. Okay, so what is the solution to this problem? Well, you actually already know the solution to this problem. We talked in chapter 3. We said if you're measuring molecules, we normally use a continuum source. But if I'm measuring atoms, then I use a line source. So we need to use a source that's made of the same material as whatever I want to measure. So if I want to measure sodium, I need to use a sodium line source. If I want to measure lead, I need a lead line source. If I want to measure iron, I need an iron line source. So the most common, for example, we could use a sodium vapor lamp. And so here we're going to use electricity to excite the source, and then it will give me the absorption I need just for that element. You know, I excite the sodium, and it'll give me light to excite sodium atoms. Now, for these kinds of sources, the bandwidth of the source is much, much less than the bandwidth of the sample. We do these at fairly low pressure and low temperature, so we don't have that problem. Okay, so there's actually two sources that are commonly used in AAS. The first one is called a hollow cathode lamp, and we abbreviate that HCl. Okay, so you should know this name and this abbreviation. So this is a tube that we fill up with neon or argon gas at a low pressure. And then we have a cathode that's made out of whatever I'm trying to measure. If I'm measuring sodium, it's made out of sodium. If I'm measuring iron, it's made out of iron. If it's measuring lead, it's made out of lead. Okay, so what we do then is apply a voltage, a large voltage between the anode and the cathode. And what happens is some of this inert gas in here, like argon, gets ionized. And that argon then knocks into the cathode with some energy. And some of the metal atoms will then come off. Okay, this process is called sputtering. Okay, that argon hitting the cathode and knocking out metal ions. Now, some of those metal ions will be excited. Okay, so they're excited, and then they will come back to the ground state, and they will emit light. Okay, and this is the light that I'm then going to put into my sample. So that's the hollow cathode lamp. This explains the process that I just explained, how that works. So here it is in words. And again, the cathode is made out of whatever you're wanting to measure. You want to measure calcium, it's made out of calcium. You want to measure iron, it's made out of iron. So we need a different lamp for each element. So remember, I said that AAS can only measure one element at a time. Okay? And there's two reasons for that. Here's the first reason. Okay? Every element needs a different source. If my source gives me the light to excite sodium, then I cannot use it for calcium or iron. Okay? So every element needs a different source. That shape of the cathode is that way because it maximizes the probability that those atoms that are being sputtered will then deposit back on the cathode. And then it makes all the light come out in the right direction. So here's a picture of what a couple of HCl, hollow cathode lamps, look like. Okay, and in both cases, the light will go out towards the end here and into your sample. Okay, that's the first kind of source. The second source is called an electrodeless discharge lamp. Okay, kind of a long name. It's abbreviated EDL. And you do need to know the name or the abbreviation for these two sources. Okay, so this is a little bit different. Now you're going to have a tube, again, with an inert gas, usually argon. And then instead of a cathode, you're going to have the metal or the metal salt inside there. Now, this one doesn't use a voltage. It's going to use RF frequency. So the RF frequency will make the gas turn into ions. So again, the argon gets ionized, and then the argon hits that metal salt that's in there, and then you're going to get some excited metal ions, and then you will produce light from that metal ion. Okay, now these have a higher intensity than the hollow cathode lamps, but they're not as reliable. They break more easily, and they are more expensive. So usually we only use these if you want to look at an element that does not make a good cathode. For example, these elements, selenium, germanium, arsenic. For those, you would use an EDL. Okay, so the instrument. So far we've looked at the source, and you should now know there are two sources. What are they? Hollow cathode lamp and electrodeless discharge lamp. So HCl and EDL. You need to know the name of those two sources. All right, next we want to look at the sample introduction. Okay, I need to get my sample into the instrument. So for the method to be reproducible, the sample has to be representative, and it has to be reproducible, that I can always get the same amount of sample into my instrument. And this is actually the hard part for many AA methods, especially if your sample is a solid or a refractory sample, something that is very stable at high temperatures, it's hard to dissolve. This can be very difficult. However, if you can get your sample into a solution, or if your sample is a gas, then the introduction is extremely easy. And most AA is done on liquids. So let's look at how do we get liquids into my instrument. So we're going to use something called a pneumatic nebulizer. So this word pneumatic means air, So what a nebulizer does is it converts your sample into small, tiny droplets using high pressure gas. So you have a high pressure gas, it hits your sample, and the force breaks your sample into small droplets. Okay, and this small droplets, the mist, is called an aerosol. And then once you get your sample into these small droplets, then the gas will carry your sample to the next step for atomization. Okay, so this is called a nebulizer. Now, actually, you probably have experience with this. Have you ever, taken a drink of water and then somebody says something that makes you laugh and you go, and that water in your mouth goes spraying out into droplets, okay, from the air in your lungs? That is nebulization, okay? So air, high pressure air hits your sample, breaks it into particles. Now, notice in this picture, some of these particles are big and some are smaller. They're not all the same size. And this is pretty accurate. You get different size particles. So often what they do is they put a bead here for those particles to hit. Remember, they're being carried by high pressure. And so when they hit that bead, that will help all the particles break up a little bit more, and you get a more uniform mist, a more uniform aerosol. Okay, so that's nebulization. All right, now I get my particles into this mist of small particles, and now I need to atomize them. Okay, I need to get them into the gas phase as single atoms. So this is absolutely critical because in AA, this guy right here, that's the one that's going to absorb the light. That's the thing I'm trying to measure. Okay, so there are several processes that occur. So we've already seen the first one, nebulization. We're making these small particles. Okay, then we need to do something called desolvation. This means remove the solvent. And then I need to volatilize it or vaporize it. I need to get it into the gas phase and then finally form atoms. So if you have a high temperature source, for instance, a flame, the first thing that happens is that mist, that nebulization product, goes into the flame. And the first thing that happens is desolvation. So you have wet droplets, small droplets of your sample, and that you remove the solvent. So they become solid particles. Now this happens very quickly, these steps that they happen much quicker than I can explain them. All right, once you have the solid particle, then you need to turn that into the gas phase, okay? And then the next thing is you need to break that apart and atomize this so that we get this single atom, free atom, in the gas phase. Now, for atomic absorption, remember that's what we want, ground state neutral atoms. This is what we want. And to do that, I need a temperature of about 2,000 to 3,000 degrees K, which is the temperature of a flame. Okay, so I take my liquid sample, I nebulize it, I get it into the flame where it's desolvated, then it's volatilized, and then atomized. Okay, so right here, this is what I want. Now, sometimes there's other chemistry that goes on in that flame. One thing that often happens is that free gas atom will combine with something else in the flame, often oxygen. This is very common, and form some kind of oxide. Sometimes that free metal ion can become ionized, so you get M+. And sometimes you may even get excited M. Okay, now all of those three things we do not want. Okay, remember, my signal comes from M absorbing the light. So if my sample is M excited or M+, those do not absorb the same light that M does. Okay, so this is what I want, M in the gas phase. Okay, now, again, how do I atomize? What do I use to do this process? This is the process. Well, as I've already mentioned, the most common way to do this is to use a flame. So if we use a flame, sometimes you'll see FAAS, that's flame atomic absorption spectroscopy. So in a flame, you will need an oxidant and a fuel. So an oxidant can be oxygen, air, or NO. The fuel is usually methane or hydrogen or C2H2. It's called acetylene. And notice that depending what your fuel and oxidant is, you can have different temperatures for the flame. The flames can vary between 1700 to 3100 C. Okay, so we need to talk a little bit about what does a flame look like, the structure of the flame. And the size of these and the appearance of the flame changes depending on your fuel, your oxidant. So the first thing we have is down here, the part of the flame where it's often blue, because that's where you see carbon burning or CH bands. This is called the primary combustion zone. So this is where most of your sample is burned up, here in the primary zone. Okay, then right above that is this region called the interzonal region. Okay, this is where combustion ends. So by the time your sample gets here, now we have that M in the gas phase. And this is usually where I do the analysis. So I shine my light through this part of the flame. Okay, and then there's the secondary combustion zone. So as M moves further out, it now comes in contact with the oxygen out here in the air. And so this region is where you start getting that oxides that are forming. Okay, so those are the three zones for the flame. Also note that the temperature of the flame is different depending on where you are in the flame. As you go up, the temperature gets higher, it starts out low, then gets higher, and then gets lower. It also changes as you move from side to side. Now, this is important because the temperature affects that atomization process. It will affect how quickly your sample gets converted to M. Okay, now when we look at the flame, we get something called an absorption profile. And what we find out is the most sensitive part of the flame, or the best part of the flame for AAS, is different for different elements. Now, why is that? Well, remember in atomization, there are a couple of processes that happen. The one we want is we want that sample converted to M in the gas state. And this is what I'm trying to measure. But remember, M also can form oxides. Almost everything will form oxides as it comes into contact with oxygen. So what we see, for example, with magnesium, okay, now notice we're looking at this with flame height. So we're moving up in the flame. So we start out low in the flame, okay, and there's a low signal. And then as I go higher in the flame, the signal for magnesium gets higher. So when I'm reaching this point, this is where I've got most of this in as M. Then as I keep going higher in the flame, the signal drops off. Okay, now what's happening there? Well, that's where the oxides start to form. Okay, now silver is very different. Notice when I'm low in the flame, the signal is low. And then as I go higher, the signal keeps getting higher and higher. Okay. Silver does not like to form oxides, which means the longer it's in the flame, the more silver you get. So to measure silver with the maximum signal, I want to be high in the flame. For magnesium, I want to be in the middle. Chromium, exact opposite. Start off with a high signal. So chromium very quickly goes to M, and then as I keep going up, chromium converts to the oxide. So the signal drops. So for chromium, I want to be measuring low in the flame. So notice 3 elements, 3 different places where I get the maximum signal. So you have to optimize your burner position to get the highest signal for each element. And usually you will actually take a sample when you're doing AAS. You'll take a standard with magnesium and you'll take your burner and you'll move it up and down, watching to see where do I get the maximum signal. Okay. So this means it's difficult to do multi-element detection, okay, because every element has a different optimal position in the flame. Okay, so if you remember, I told you that AAS, line source AAS, only can measure one element at a time. And I said there are 2 reasons. Okay, what are they? First one, the source. Every element needs a different source. Second reason, burner position. Okay, the optimal burner position is different for every element. Okay, so that's the flame profile. Now, the most common flame is we use something that's called a laminar flow burner. And it looks like this. So notice the oxidant comes in, the fuel comes in, and your sample comes in, and they all get mixed. And then they go up, and there's these things are to get rid of the biggest particles, okay? But then that mixture comes up here where it burns. Now, these flames are pretty inefficient. Actually, only less than 5% of your sample actually gets up here. Most of the sample actually comes out through the waste. So only a small amount of sample gets up here where it goes through the flame. Now, this kind of flame are very stable. And notice that this showing you the burner with it not lit. This is it. It's lit. They probably put, I think, strontium in this so it burns red so you can easily see the flame. So here would be your light source. And then you're shining your light source down the length of the flame. And notice that the path length for this, okay, the length of the flame is pretty long. It's 5 to 10 centimeters. Okay, that means you're going to get a higher signal because this is absorption, Beer's law. Absorbance is proportional to ABC, path length. So longer path length will increase your signal. Okay, so that's the laminar flow burner, the most common type of flame, very stable, quiet flame. All right, so as I said, the most common type of atomizer is a flame. So let's look at some properties of the flame. So the flame is best for reproducibility. Okay, now this word best means I'm comparing it to something. So what am I comparing it to? I'm comparing it to other kinds of atomizers that we haven't talked about yet. Okay, but the flame is very reproducible. It's the best one. However, it's not very efficient. So it's not as sensitive as some of the other atomizers. Now, why is it not efficient? Well, two reasons. One, remember I said most of the liquid never makes it to the flame. Most of the liquid just goes out as waste. So we lose a lot of our sample. Another reason is the sample spends a very short time in that flame. You know, it goes up into that flame and quickly burns out. So that sample is only there about 0.0001 seconds. So very short time to try to detect this, okay, which lowers the sensitivity of the method. However, this is still a pretty sensitive method. This method, you can get detection limits part per million to part per billion. So notice that's 10 to the -6 to -9 grams. Okay, so, you know, I said it's not the most sensitive, but this is a sensitive method. These are very low concentrations. But there is a method that is more sensitive, can go even lower than this. So let's look at that. So this one has two names. It's called electrothermal. So electro means we're using electricity to heat it, or graphite furnace. Okay, and you can see it's abbreviated. Often graphite furnace is probably more common. So GFAAS. So here what you have is a little tiny carbon tube, graphite tube made of carbon. Notice 5 centimeters by 1 centimeter inside. So these are small little tubes. And so we're going to put my sample down inside of that tube. And then I'm going to heat that tube. And so my sample will be in here. It gets heated and it will get atomized. And then the light comes through and we'll measure the absorption. Okay, now actually it's not as simple as we just heat it. It's actually a 3-step process. So I put my sample down in that tube, and the first thing I do is I use a fairly low temperature, maybe 100 degrees, to dry it. I want to remove the solvent. And that takes 10 to 100 seconds. Then I increase the temperature to maybe 500 degrees. And what this will do is destroy any organics. All the carbon gets burned up in your sample. And then finally, I take the temperature and I take it all the way up to maybe 2,000 degrees, maybe hotter, very quickly. And that will then atomize your sample. So we have these 3 steps that we do. Okay, so going back to this picture, I put my sample in here. And we said the first thing we do is dry, and the water comes off. So notice there is some argon gas that's flowing through this tube. So that argon gas is pushing that water out, because we don't care about that. Remember, we're trying to measure M. Next, we char, or ash. 500 degrees, out comes the organics, and then we push that out. And then 2,000, now I get M. And my light can measure that. So this internal gas flow is pushing out things that we don't want. It's also keeping oxygen from getting inside so that we don't get oxides that form. There is also some argon that flows around the outside of the tube. That's to keep the tube from burning up. Okay, when we get to 2,000 degrees, that's very hot. We don't want to destroy the tube. So the argon around the outside helps cool things. So here's an example of a calibration that we might do for this. So notice we have this 3 standards that they did here, and here's their signal. Okay, these 3 peaks are all from my sample. So notice in the dry, that water's coming off, so that water's in the light beam, and so we're getting a signal. And then when I ash, I get all that carbon, and that's in the light beam, so I get a signal. But those are not the signals I want. These are just kind of all garbage. Okay, the one I want is this one that happens during atomization. That's when my M gets formed. So what would be the concentration of this sample? Well, notice from the standards, this signal is very close to this one. So it's about 0.05 micrograms per milliliter. Okay, so that's how the graphite furnace works. Now, one other thing that almost always they do with these tubes when you buy them, they will have a platform in them that's called a Lvov platform. So that when you put your sample in, you actually put it right here on the platform, not right on the edge of the tube. Okay, and the reason for this is when you're heating this tube, these outsides, the borders of these tubes get much hotter than the inside, and you get some uneven heating. So by putting your sample on this little platform up off the tube, it makes things occur in a more reproducible environment. So using this improves the precision of the method. So almost always these tubes will have this little platform in them called a Lvov platform. Okay, so let's talk about the performance for this graphite furnace. So they can analyze very small sample sizes. Flames, you need a lot more sample because you're sucking it all through your flame very quickly. So notice we can measure down to 0.5 microliters. So really small amounts of sample can be measured. As I said, the sensitivity is much better than for a flame. Okay, notice we can go part per billion to part per trillion. Okay, remember the flame was part per million. So this is much more sensitive. 3 to upwards 6 orders of magnitude. Very sensitive method. And the reason this is so sensitive is, one, your entire sample is analyzed. None of it goes to waste. And then the sample is actually in that tube for maybe up to a second. Remember, a flame, we said 10 to the minus 4 seconds, gone. So in the flame, it has to absorb the light very quickly. In the tube, much longer to absorb the light, which makes it a much more sensitive method. Also, another reason this is much more sensitive is we get rid of most of the background, okay, the matrix effects. You know, there's very few interferences here. Because remember, first we dry it, all that out. Then we char it, all of that's gone. So we're getting rid of the interferences and then measuring just M. In the flame, they're all there together. So lower backgrounds, more sensitive method. Okay, and the graphite furnace can do solids. You can't do a solid in the flame. You know, you would have to first get it into solution and then do it. But you can directly put a solid inside that little tube. Okay, so clearly this method has a lot of advantages, but it also has a few disadvantages. The precision is much worse than a flame. That's because of the lower detection limits. Lower detection limits will always have worse precision. It also requires much longer to analyze your sample. You know, you have those 3 steps that take 2 or 3 minutes, and then that little tube is really, really hot. So then you have to wait for it to cool off before you can take it out and do another sample. So a flame, very quick. You know, put your sample in, done. Sample, done. So flames, you can analyze lots of samples quickly. Graphite furnace, much, 5 minutes per sample, so much, much slower method. Also, the dynamic range is much smaller for this. Notice 2 orders of magnitude, which means there's only a narrow concentration range I can measure. With a flame, I can measure a much bigger region. Okay, oh, and this isn't on the list, but also the graphite furnace is much more expensive. It's more expensive to buy, and it's more expensive to operate. So it's a much more expensive method. So when would we use graphite furnace? Usually only if the flame doesn't give you what you need. You know, if the detection limits for what you need are not okay with the flame, then maybe you would use graphite furnace. Okay, but this is much less common than flame. Okay, so we have looked at the source. There are 2 sources. They are HCl and EDL. We looked at the introduction device. That's the nebulizer. Atomization, we looked at 2 ways. Flame, graphite furnace. All right, we need to select the wavelength. That's going to be a good quality monochromator. The detector, we're measuring very low concentrations. So the detector needs to be very sensitive. So again, most common is going to be PMT. You could use a CCD, but again, this is much more expensive. And we're only measuring 1 element at a time, so we don't need multi-channel. So PMT is going to be the most common. Okay, now really quickly, I mentioned there were 2 kinds of AAS, line source and continuum source. Now this continuum source instrument is much more powerful, but it is very expensive, and you will probably never use it. So I'm not going to ask you about the continuum source on the test or on the quiz. If there's a few of you that are interested, I will just tell you very quickly, how can we use a continuum source for AAS? You know, we said that causes big problems with deviations from Beer's law. So to use a continuum source, you need a really high quality monochromator. You need a resolution of 2 picometers, 10 to the minus 12. So you need a really good resolution. You need a source that gives you all of the wavelengths and is more intense than a hollow cathode lamp. And then you're going to need a multi-channel, very sensitive detector. So they have solved all these problems. Turns out you can use a xenon arc lamp at a very high temperature that will give you all of these lights. You can use a special kind of monochromator. Here's its name that has that high resolution, and you use a CCD detector. And the power of this method is you can detect multiple elements at the same time. Okay, not just one, you can detect many, many elements at the same time. Okay, so that's the continuum source. Now again, I'm not going to ask you about that, but if you were interested. Okay, we will go on and talk a little bit more about the instruments, but it is past time for a break. So we will go ahead and stop here for a break and then come back in 5 minutes. Okay, for those of you that came late, I did ask for attendance. So if you have not sent me your name and student number in the chat, you need to do that. However, I will remind you that class starts at 8:30. And so if you haven't done that, you are late. For those that are watching by video, you can send me an email or you can send me a message in Rain if you figured out how to do that. So send me an email and tell me the word mountain. Mountain, okay? Okay, all right, so going on now, we want to look a little bit closer at the instrument. So here are two designs for line source instruments, which is all we're going to be looking at from here on out. So notice they have the source, they have a flame, they have the monochromator, and then a detector, which is PMT. Now, as you look at these two, what's the difference? What's the difference? Okay, well, notice the bottom one, some of the light goes through the flame and some of it goes around. So this bottom one is an example of a double beam instrument, a double beam instrument. All right, now we need to actually talk about this whole process and several problems that might come up. So remember, we're trying to measure absorbance. So I've got my sample and I get it up here in the flame as M. So I've got it in here, I've got my M. So I've got my light source that's also M, and it's shining light through the flame, and I want to measure absorbance. So I want to measure the difference between PO and P. And I'm going to have a monochromator and a detector. Now, there are several different problems that can happen while you're making this measurement. Okay, the first is some of this light from the source might be absorbed by the flame. You know, there are things in the flame, and so just the flame itself, without your sample, some of the light might be absorbed. So we have to correct for that. And you actually should know how we would do this. This, we would use a blank. Okay, that will correct for the light. All right, second thing that might happen is the intensity of this source could change with time. So you should also know how would we solve that problem. The same way we solved it in chapter 4. This one we would use double beam. Okay, next thing that could happen. The flame will emit light. It's a flame. Of course it emits light. Now, we only want to measure light from the source. We don't want to measure light from the flame. Now, there's two kinds of light it can emit. The first is it can emit light that's a different wavelength than the source. You know, say we're looking at 500, you know, and maybe the flame gives us some 400 or 600. So it gives us a different wavelength. It could also give us light that is the same, that's say 500. Okay, and we actually deal with these two different ways. So the first one, the light that's different from the source, we use the monochromator. Remember, the monochromator's job is to choose the light that gets to the detector. And if we're measuring 500, that's not a very good zero over there, then we select the monochromator to only let 500 through, which means the 600, the 400, the 450, it does not get through the monochromator to the detector. So that's easy to deal with. Now, what about the light that's the same as the source? And you might think, oh, probably it's really not going to be very much light that's exactly 500, right? Well, actually wrong. Remember what we're doing, okay? We're shining this 500 into the light, into the flame, and M absorbs that light. So then we get excited M. And we want to measure, how much of that light did it absorb. But this excited M, what is it going to do? It's excited. It's going back to the ground state. And when it goes back to the ground state, it emits light. And what light does it emit? That same 500. Okay, so now this 500 that's coming from the flame, the excited atoms, that's going to go to the detector. The detector's going to see that. But I don't want to see that light. Remember, the light I want to see is only the light from the source. So this is actually a big problem that we have to fix. And we fix it using something called modulation. Okay, modulation. So what modulation is, we use either a chopper or a pulsed power supply to make my source light look like this. We're basically turning it on and off, on and off, on and off. Okay, and this is going to eliminate that light that is emitted from the flame. Okay, because the source looks like this, on, off, on, off. The light that's coming from the flame is all the same, not modulated. Now, both of these signals get to the detector. They're both 500. But now there's two different kinds of signals. One is modulated, one is not. And with electronics, you can actually pull out the one from the other. So the total light the detector sees, it's going to see both the flame and the source light. But we can pull out the flame light because it is not modulated. So now going back to that spectrometer, notice this one has a power supply, a modulated power source. That's making that power source that square wave I just showed you so that we can correct for that interference. So with a single beam instrument, you will take a blank and run that through your flame, and then you set that to be 100% T, or your zero absorbance. Okay, the other type that we looked at was the double beam. Okay, now notice this one has a chopper to modulate the signal, and it's double beam. So the light goes through the flame and then around the flame, through and around, back and forth, back and forth. And remember, what is the purpose of the double beam? The double beam corrects for changes in intensity or power of the source as that changes with time. Because we're comparing this light and this light, we can correct for that. Notice the reference beam doesn't go through the flame. Okay, so it does not correct for any light that's absorbed by the flame. But remember, that's the job of the blank. Okay, all right, so that's the double beam instrument. Okay, so a little bit complicated, but everything nicely explained here, how we deal with all of these different problems. Okay, now there are actually some interferences we have in AAS. Okay, in addition to how the instrument works, there's some interferences. And there's two kinds. So one is called spectral. And this is when the absorption spectra overlaps your analyte absorption, or there's emission that overlaps. You have your sample and something else absorbing or emitting at the same wavelength. That's called spectral interference. And then the other kind is called chemical. And this is where there is something either in your sample or maybe in the flame that's causing changes in the atomization. It's either making the atomization higher or lower, although it's almost always lower. Okay, so let's see, how do we deal with these problems? Okay, so spectral interferences, remember the lines from the HCl are very, very narrow. So we're probably not going to have two lines exactly in the same place. It's pretty rare. But if it does occur, then we just choose a different line. Okay, for example, I'm trying to measure aluminum that absorbs at 308.215 nanometers. And there is also vanadium in my sample. And vanadium, notice it absorbs very close. These are 0.004 apart. So these two lines are on top of each other, and I can't tell them apart. So the solution is easy. Find a different line for aluminum. So aluminum has another line at 309.27, and now we can measure just aluminum with no vanadium. Another thing, sometimes your flame will scatter light, and that will lower how much light is getting through the flame. If it's just the flame doing this, then the blank will correct for this. All right, and then the third kind of spectral interference that we can have is sometimes there's combustion products. Something forms in the flame, and it has a broadband absorption that interferes with your signal's absorption. So for example, I'm trying to determine barium, okay? But my sample also contains calcium. So I'm trying to measure this barium line right here. But in the flame, there's chemistry happening. The calcium in your sample is combining with the oxidant from the flame, probably oxygen, and forming calcium oxide. Now, calcium oxide has an absorption spectra like this and also an emission spectra, which means I'm trying to measure barium, but that calcium oxide is also going to absorb and emit at that same wavelength. So I cannot get a good measurement for barium with this situation. So if you have this kind of interference, there are three things you can try. The first thing is try a higher flame temperature. Maybe you can make the calcium hydroxide break up so it's not there. Second thing, find a different barium line, that is outside of this. If you can find a barium line over here where the calcium hydroxide doesn't absorb. And then the third thing, the one that's commonly used, is to use something called a background correction. So this is actually a way to actually take this signal and subtract it out of your sample. Okay, and there are a couple of methods to do this. They're a little bit complicated, so we won't talk about the methods. I think one of them might be explained in your book, but you should just know the word background correction is a way to correct for spectral interferences. Okay, now the other kind of interference, chemical. Now, actually, these kind, chemical, are much more common than spectral for AAS, especially flame AAS. And usually, again, it causes a change in the atomization behavior of the analyte. Usually, the atomization signal is lower. And often one of the things that causes this is anions that will grab a hold of that metal ion and make it hard to atomize. Okay, so this will be common if your analyte has a very complex matrix, like seawater. If we were trying to measure iron in seawater, there's lots and lots of ions that can interfere. Okay, so there are actually some different things that you can try if you have chemical interferences. Let me give you one example. So calcium in the presence of phosphate. Phosphate really likes calcium, and so it will bind to it pretty strongly. And calcium phosphate is less volatile than calcium chloride. Okay, so what that means is calcium chloride in a flame is easy to atomize. This calcium phosphate ion is hard to atomize. So that means the more phosphate is in your sample, the lower your calcium signal will be. For example, if you had two samples and one, the source of calcium was calcium chloride, and the other one was a calcium phosphate compound. Okay, and that charge isn't balanced, we'll make it this. All right, these two, say they had the same concentration, 10 parts per million of calcium. When you do the measurement, the signal for this one will be much higher than the signal for this one, because that calcium phosphate does not want to break up. Okay, so you're going to get a bad result. Okay, now there are several things you can try to fix this problem or other chemical interferences. So I'm going to give you 5 things. Now, you should know that all of these things do not work for every situation. These are things you can try. Some of them will work for some situations, but they may not work for every situation. Okay, so the first thing you can do is, again, try a hotter flame. If we got the temperature higher, maybe we can get that calcium phosphate to break apart. So that's one thing you can try. The next thing you can do is use something called a releasing agent. So this is a cation that's going to interact with whatever is interfering. For example, in the calcium phosphate example, if you add lanthanum or strontium to your sample, these two ions really like phosphate. They like phosphate more than calcium. Okay, so what happens is, you've got calcium, you've got phosphate, and here's the lanthanum or strontium. So those are actually going to bind the phosphate. So that releases the calcium to be free so that you can measure it. Okay, because these guys, the releasing agent, has taken out the interfering ion. Okay, another way to try, thing you can try is, instead of taking out the interfering ion, you use something called a protective agent. So this is something that is going to actually grab the calcium and protect it from the evil phosphate. 2 common compounds that are used. This one, which is 8-hydroxyquinone, and this one, EDTA. And both of these guys are very good at binding to metal ions. And EDTA especially loves calcium. So here you got the phosphate trying to grab the calcium, but here comes EDTA. EDTA is more powerful than phosphate, so it kicks the phosphate out, and it says the calcium is mine. And so now it's got a hold of the calcium. Now it turns out EDTA is willing to release the calcium when you get it into the flame. Phosphate won't let go, but EDTA is easier to volatilize. So then it will let go of the calcium when it's time to measure it. Okay, so that's a protecting agent. All right, 4th thing you can try is to try to match the matrix of the standards and the samples. So if phosphate's causing a trouble in your sample, then we put phosphate in everything. We put it in my blank, we put it in my standards, so that everything behaves the same way. Okay, now the problem with this is often you do not know what the matrix is. You don't know what is causing the interference exactly. So we have a way around that. Remember standard addition? So standard addition is where you take your unknown that has the interference, that has the problem, and we put that in your blank, and we put it in every standard, and now everything behaves the same way. Everything has the same problem, and now you can get a good measurement. Okay, so 5 things that you can try to do to fix chemical interferences. Okay, and then one other kind of interference we need to look at is something called an ionization interference. So remember, we said we are trying to measure M, and we're got a source that gives me light to excite M. But sometimes M is easy to form ions. And if I have this light from my source that came from M, okay, and I've got my light that's coming, this light will be absorbed by M, but M plus is a different species. It will not absorb that light. Okay, so that's a problem. Your signal is going to be lower. All right, so the signal comes from the neutral analyte, and if it becomes an ion, then you're going to get a lower signal. And this is a serious problem for the alkali and alkali earth metals. Okay, so those are sodium, potassium, lithium, calcium, magnesium, strontium. These are all pretty easy to ionize. All right, so the solution for this is to use something called an ion suppressor. So what this is something that is easily ionized, more easily than your sample. And a common example is if I'm trying to measure sodium, I will add potassium. So the potassium is easier to ionize. So the potassium will make lots of K plus and lots of electrons. Now my sample, sodium, up here, I need this as Na. Well, these lots and lots of electrons from the potassium is going to take that equilibrium and shove it back this way so that the sodium stays as sodium neutral and not the ion. Okay, so ionization interference, you use an ion suppressor. Okay, so now we need to talk about the sample preparation. So most of the time we need our sample in a clean aqueous solution. We've got to put it through these small tubes and turn it into small particles and then into the flame. But most samples are not clean samples. Often I want to measure the metal in soil, dirt, or plants, or animal tissue, petroleum products, things that are very dirty. So before I can put my sample into the instrument, I have to do complicated procedures that often take a lot of time and are actually much harder to do than doing this measurement. Often you have to do things like heat it in a concentrated acid and then centrifuge it and filter it. And often that will cause more errors in your method. So again, that's one advantage of the graphite furnace, the electrothermal, is I can use these dirty samples directly. I don't have to get them cleaned up first. However, getting a blank and calibration can be hard on these complex samples for that. Okay, now AA should obey Beer's law. Okay, remember Beer's law, A is equal to ABC. So the absorbance should be directly related to concentration, but often it's not. So you cannot assume that it follows Beer's law. You always have to do the calibration curve, make the standards and measure their signals and then get your calibration line. You also have to be aware that atomization changes. That can be a major variable. Sometimes, that's that drying up your sample, it's not always the same rate. So your instrument can change from hour to hour, day to day. So you should always be running standards to make sure the instrument's running the same way. The best method is actually to run a standard, then your sample, and then a standard, so that your instrument is operating correctly and in the same way. And as I already said, often we use standard addition to compensate for matrix effects. Okay, so the applications, as I already said, we use this method to measure metals and metalloids. There's more than 70 elements from the periodic table that you can measure with this method. In theory, you would think we should be able to do nonmetals, but most of those lines are in the vacuum UV, so we can't easily measure them. So this method is used for metals and metalloids. Detection limits, as we already said, the flame usually about 1 to 20 parts per billion. The electrothermal analyzer, much lower, 0.01 to 0.002. So electrothermal atomizer, much more sensitive. But precision, the flame is much better. Usually you can get 1 to 2% precision. The graphite furnace, 5 to 10%. Okay, so applications. It is used in all kinds of different areas. This looks like a long list, but it's actually a short list. Many, many different areas. And again, we use this method to measure metals and metalloids, okay, in various samples. Okay, so that is chapter 5. All right, so you should make sure, like you should for every chapter, that you look at all of the homework problems at the end of the book. Okay, so now we've finished chapter 5. So next week on Thursday, November 12th, we will have our second quiz. Okay, so we're going to have that Thursday afternoon at 1:35 p.m. China time, and it again will be open book, and you will have 25 minutes to complete the quiz. Again, this quiz will be on RAIN. You need to use a computer, not your phone, and you need to have your camera on during the quiz. Many of you did not have your camera on for the practice quiz. And I'll tell you, the university for the final exam requires that you have the camera on. If you don't have it on, your final won't count. So you need to learn how to do this now. So cameras have to be on during the quiz. As always, for a quiz, you should not consult other people or the internet. You can use all your books, all your notes, but you shouldn't use anything beyond that. Again, you need to study like it's closed book. You do not have time to go find all the answers. And you need to make sure you pay attention to time. You can't decide, oh, later I will go answer the questions. Answer them as you go, and then if you have extra time, you can go back and change them. But if you wait till the end and your time is up and you turn in a blank quiz, then you get a 0. So pay attention to time. Okay, the types of questions this time for this quiz, there'll be multiple choice. One of those is more than one right answer. And it will tell you, choose all that are correct. Okay, the others, one answer. There's 4 points of choose one, where you just have 2 choices, and 7 points of short answer. There will be one matching, only 4 points, and you should again give the answer as a number and a letter. We're getting better on the quiz, but some people are still trying to do it their own way and not what I'm asking for. So for this quiz, everything can be answered in the system. No pictures for this quiz. Okay? Everything you either click the choice or type it in the box. Again, you're using your computer. If you did the practice quiz, you should maybe bookmark this site so you have it and the system will already know you. So the quiz starts at 1:35. And again, you will need to verify your ID and turn on your camera. If you verified your ID this time, it probably will still be there, but you need to sign in before. So maybe at least 5 minutes early, you need to sign in and put in your ID and turn on your camera so that at 1:35 you are ready to start the quiz. If you show up late, like a lot of you do for class, then you're losing quiz time. You will not get it back. If you show up 10 minutes late and then mess around with your ID and 15 minutes are gone, you're going to be in trouble. So early before the quiz, sign in, and then be ready to start at 1:35. Okay, and just some notes on the practice quiz. Again, your camera has to be on for the entire quiz. The matching, again, it's getting better, but you need to have a number and a letter. This is the form your answer should be in. 1C, 2E, 3D. Some of you did 1C, 3D, 5F, 2E. They need to be in order, and some of you only had a letter. Some of you tried to get the words. So this format. This won't happen for this quiz, but from the practice quiz, if the instructions say submit by picture, you must use a picture. That last time the calculation on the practice quiz was simple. So some of you just did it in the box. You can't do that. If I say submit by picture, you have to use a picture. And you have to include your name and student number. Now, I know you're thinking, oh, why does it matter? Why can't I do it my way? The teacher, she's so mean and, just so picky. And there's a reason for that. Engineers must be able to understand and follow instructions and procedures. If you're working on an engineering system, you cannot make up your own way to do it. There are established procedures and you have to be able to follow them. Okay, I'm not asking you to do anything that's hard, but these skills, following instructions, following the procedures, are critical for your major if you are going to be competent in your field. Okay, so I'm really serious. Follow my rules. That's just the way it's going to be. All right, and finally, there were several of you that did not turn your camera on the quiz. You need to do that. And there were several that did not take the practice quiz. The quiz is not yet closed, so you need to take it to make sure you're familiar with the system. Now, I know some of you that didn't take it yet, you had some problems and you've communicated with me, and that's okay, but several of you have not even attempted it. So that needs to be taken care of immediately, those quizzes. I will just make one note about the practice quiz. And again, the score from that quiz doesn't count. You got a score, but you don't get those points. You get either yes, you did it, or no, you didn't. You only get that kind of credit. But there was one question that said, dogs are always bigger than cats. And 60% of you missed that question. You said, oh, that's true. It is not even close to true. There are lots of little dogs out there, and that, cats are bigger. And that's not even counting the great big cats that are definitely bigger than dogs. Okay, so that question was very false. Okay, so next Thursday, second quiz, not practice, a real quiz. Make sure you're signed on, ready to start at 1:35. And then Friday morning, we'll have our normal class at 8:30, and we'll be starting chapter 6, which is a new chapter, new topic, electrochemistry. Okay, that is it for today. So I will stay around and